alkyl halides can be converted into organometallic compounds. These are organic compounds where you at least you've got a carbon bonded to a metal. A classic example is the so-called Grignard reagent. The way you make this is you take methyl bromide or some alkyl bromide. It can be just about anything. Treat it with magnesium metal in the presence of ether, right? And these ethers are important for the reaction. And what happens is you get this reagent where you've got a bond now between C and magnesium. Right? And this guy's called the Grignard reagent. This guy, he's called methyl magnesium bromide. Right? And the thing about it, it exists in this resonance structure where the negative charge can be on carbon, and you put the positive charge on magnesium. So what happens is it acts as a carbanion, right? There's not actually a carbanion in the solution, but this is how this guy reacts. And they're both strong bases and strong nucleophiles. The mechanism, it's complicated. There's a radical transfer where your alkyl bromide reacts with magnesium. You end up with an alkyl radical, right, and a magnesium radical cation. There's a coupling step where now you form the C metal bond, and again forming your Grignard reagent. All right, there's a bunch of rules. Well, not a bunch of rules, but represent the general form is that Rx, where X is a halogen, I BrCl, F is not allowed. Fluorine never behaves like anybody else. Magnesium in anhydrous ether, it's important that it's anhydrous, forms the alkyl magnesium halide. R can be alkyl or alkenol, can be aryl, can be just about anything. Right? All these would be allowed alkyl halides to form Grignard reagents. All right, so here we have aryl chloride, we have chlorobenzene. We would draw this showing the formation, right, of the Grignard. We call this phenyl magnesium chloride. Right, and it's a strong base. So the way I think about it is it's going to behave as if there's a negative charge on the carbon that's bonded to the magnesium. That guy's a strong base, so if it sees water, it will act as a strong Bronsted base, accept the proton to become benzene, plus, I guess you'd have hydroxide as the other product here. Right, plus the other salts, right, magnesium, chloride, they'll all still be in there, but we're really not interested in them. Right, so what's the net reaction? If I take chlorine and I replace it with hydrogen, it's a net substitution reaction if I do a Grignard followed by water. All right, and this explains why it's really important to make these Grignards under anhydrous conditions, no water conditions. If water's present, like here, what happens is, remember Grignards are going to behave like anions, right? And what's the pKa of an alkane? It's about 60. It's the pKa of water, 15.7. Which way is this equilibrium going to lie? Right? It's not an equilibrium at all. It's going to go completely to products. So if a Grignard reagent sees water, it becomes an alkane plus hydroxide. And this is actually what they use. One of the uses for them is if you have a Grignard reagent, right? We're using this to represent the Grignard. If it says D2O, and remember, D is for deuterium, which is a isotope of hydrogen. It's hydrogen with a neutron. What you've done now is you've deuterated your alkane, right? So this is how we can put D's on stuff, if you've ever wondered, right? If you ever needed to put a D on there. Why must Grignards be made in anhydrous conditions? Just said this, right? In the presence of water, there's an acid-base reaction where your Grignard becomes an alkane. Really what Grignards are used for is forming carbon-carbon bonds with primarily carbonyls. So carbonyl-containing compounds like aldehydes, right, ketones. Esters work. Carboxylic acids don't work. We'll think about that right now. It'll make sense. Okay. I really want to go to the black pen. Hold on. All right. So I have an alkyl bromide, magnesium anhydrous ether. So I'm going to make my Grignard reagent, right? And this guy would be called cyclohexyl magnesium bromide. All right. Remember, it's going to behave like a strong nucleophile. So if you think of it this way, we know that carbonyls are electrophilic on carbon, right, and nucleophilic on O. And so what happens is you have nucleophilic attack. I missed. I'm hitting that carbon. Electrons go up, and draw this as a tetrahedral intermediate. So one methyl's forward, wedged, the other one's back. So this is our tetrahedral intermediate. Again, the magnesium and the bromide are floating around in here. We don't really care about them. Then if I add dilute acid, this step is called acid workup. What I do is I protonate that guy. And so what have I done? I've turned my alkyl halide and my carbonyl into a substituted alcohol. Right? So this guy, hard to see, this guy, I add, all right, this O is this O. I add a group to it. So a ketone in here, in this case, becomes a tertiary alcohol. Right, and you can do that with aldehydes. You do the same thing, except you'd have a secondary alcohol. Right, if it was formaldehyde, you'd get a primary alcohol. Carboxylic acids are a little bit different. Let's see, so if I take propyl chloride and I react with magnesium in ether, I get the propyl magnesium chloride. Propyl magnesium chloride. Still a strong nucleophile. Whoops, 1, 2, 3. This is supposed to be 3 carbons. Bad work for me. By me today. Okay, so he's still gonna, he wants to attack there. That's what we want, right? But this guy's a strong base. And this is a carboxylic acid. So what happens? It's just an acid-base reaction. So the acid's going to donate his proton, and you're going to get propane, right? Hold on, I can do better than that. Plus propane, right? So this chlorine was replaced by the hydrogen on the carboxylic acid. And then when I add acid, what happens? I protonate this guy. So the net reaction looks like, right, nothing happens to this guy, right? And this guy becomes the alkane. But really we know that this proton here is adding to the alkane. So this is an acid-base reaction. So carboxylic acids don't work with Grignards is the point. Any acidic proton. So alcohols, carboxylic acids, amines, none of those guys work. All right, last example. Here I've already made my Grignard. So here's methyl magnesium chloride. Still electrophilic on the carbonyl, so I'm going to draw my Grignard. Right, he's going to act as the carbanion. He's going to attack there. The electrons are going to go up. I'm going to form the same tetrahedral intermediate as I did in the first one. The difference here between this and this is the O. We have a leaving group. Stop. This thing, right? Here we only had a carbon, right? We had carbons on either side. Carbons almost never leave. Whereas oxygens, nitrogens, those guys can take their electrons and go. So if these electrons come back down, reforming the carbonyl, right, then I lose the methoxide anion. He leaves, right? But if I still have methyl magnesium bromide, or chloride, remember we have a bunches of these things. It's not like we can have just one in solution. This guy now can attack again, just like here, right? Same step. Electrons go up. Now we get another tetrahedral intermediate where I've added 2 equivalents of the methyl, right? 2 equivalents of the Grignard. Dilute acid now gives me this guy. All right, so the difference between aldehydes and ketones, is you add 1 Grignard, right, to make an alcohol. With esters and acid halides, things like this, you can add 2 equivalents, right? You add once, then you lose the leaving group. Now you're an aldehyde, or now you're a ketone, right? And the second one adds again. All right, so this is what Grignards are actually used for. Another kind of organic metallic compound we kind of look at is the alkyl lithium, organolithiums. And so what happens here, it's kind of similar. The mechanism is even more complicated than the Grignard, so we don't really care about it. But what you're going to make is this guy. So this guy is called methyl lithium, and he's an organolithium. He's a very strong base. You'll see N-butyl lithium. It's N-butyl lithium as a reagent used as a strong base. Other than that, you don't use these very much, but this is an organolithium, right? This carbon is still very nucleophilic and very basic. More common use is to take these alkyl lithiums and have them interact with copper iodide under anhydrous conditions. And what you get is the so-called Gilman reagent, the organocopper lithium. Right. So what have we done here? This is carbon 1, 2, 3. This is carbon 1, 2, 3. So just like the Grignard, right, we're forming a bond between a carbon and a metal. So here's a carbon and a metal. So this is an organocopper lithium, and also called a Gilman reagent, and it's more useful than alkyl lithiums. Just so don't panic about this stoichiometry. All right, like I said, it's kind of complicated. You could kind of think it. Well, you could think of it like this, but it's typically written like this. All right, so what you actually have is two copper carbon bonds. Okay, the way it works is once you have your reagent, right, this is my Gilman reagent, my organocopper lithium, right, this carbon is reactive, just like in the Grignard, right? And then if you treat it with another compound, alkyl halide, this carbon is also reactive, right? It's electrophilic. And so what you can do then is form a bond between those two carbons. Bad work by me. Right, so I'm carbon 1, 2, 3, 4. There's my new bond between carbon 1 and this carbon. All right, and then there's going to be other things, right? The copper, the lithium, the rest of my Gilman reagent. They're all floating around, but we just really don't keep track of them. All right, this lets me form a new carbon-carbon bond. So we have two ways to make carbon-carbon bonds now. All right, one is to take the acetylide anion, treat it with something like that, right? Form a new carbon-carbon bond, and now we've got the Gilman reagent here, and it works with a bunch of different reagents. So here we have an aryl chloride. Here's my Gilman, right? This is a reactive carbon. This is a reactive carbon. So what I know is going to happen is it's going to form a carbon-carbon bond like that, plus the other junk that we don't care about, right? This new carbon-carbon bond is what we're interested in. Finally, there's one more organocoupling reaction. So coupling where we're reforming carbon-carbon bonds using these organometallics, called the Suzuki coupling reaction. And it's pretty specific. You have to have an aromatic or vinyl boronic acid and an aromatic or vinyl alkyl halide. So it has to be aryl or vinyl and aryl or vinyl. There's this big mess of catalyst, right, with palladium, with a bunch of ligands around it, some other stuff in there. But what it does is it forms a bond between the two activated carbons. This is all we need to recognize. So these guys can be a little bit different. He could be, well, here's an example. Here's a vinyl one, right? So if this is aryl or vinyl, now we form a carbon-carbon bond between this carbon and this carbon. And that's, oh, that's not what happened here. Yeah, don't look at that one. Oh, tragic. Yeah, we'll just focus on this case. All right, wow. Somebody needs to go back and do this video again. What a tragedy. This come on thing. There we go. Oh, quickly, redox in organic chemistry. Remember, if you're forming CH bonds, it's reduction. If you're forming CO bonds, it's oxidation. If you're losing CH bonds, it's oxidation. If you're gaining CO bonds, or sorry, if you're losing CO bonds, it's also reduction. Wow.